In this discussion video, we will do a robber example. So this is problem number 4 from worksheet 8, and it says that a robber snatches a purse from a woman on Bancroft, 11 meters west of the corner of Telegraph and Bancroft. So Telegraph and Bancroft are two streets in Berkeley, and starts running west at a rate of 3 meters per second. A police officer standing on Telegraph 30 meters from the intersection hears the commotion and starts chasing after the robber, running north towards the intersection at a rate of 5 meters per second. At what rate is the distance between them changing after 3 seconds? So pause this for 6 minutes to try it on your own first. 4, 3, 2, 1. Pause it for 6 minutes to really try this on your own. Alrighty, so hopefully you did that. Hopefully you paused it to try it on your own. So because this describes 2 scenarios, what was kind of happening initially, and then the people started running, and then it mentions what's happening after 3 seconds, I'm going to draw an initial picture and a picture after 3 seconds. So after 3 seconds. And we really don't need to know anything about Berkeley geography to answer this question, because the problem tells me everything I need to know about these 2 streets. Okay, so it tells me something about this person is running west, and then something else about like them running north. Okay, so I'm going to draw one street kind of going north-south like this, and one street going west-east like this. And remember that this direction is north, this is south, this is east to the right, and then to the left is west. Okay, so the corner of these 2 streets is where they intersect, where they meet. Okay, so let's identify which street is Bancroft and which one's Telegraph. So the problem tells me that the robber takes this purse from a woman who's on Bancroft, and that is 11 meters to the west of the corner. So 11 meters to the left or to the west. So that is here. So this is Bancroft. So I'm going to write Bank. And that must mean that the other street is Telegraph. Okay. Telegraph. So I'm going to draw another picture with some axes here. And this is Bancroft. I'll just write B for Bancroft and then T for Telegraph. Okay. So we have this. I'm going to call this spot R, for this is where the robber is initially. So where is the police officer? Well, the police officer is standing on Telegraph, 30 meters from the intersection. So that might mean maybe they're 30 meters above the intersection to the north, or 30 meters to the south of the intersection. And then it says, well, they hear what's going on, and they started chasing after the robber, and they're running north towards the intersection. So that must mean that the police officer is somewhere down here, if they are running north to get to the intersection. Okay, so the robber is going to be running west. It tells me they're running west because they want to run away from the police officer. And the police officer is running north, it tells me, towards the intersection. Okay, so after 3 seconds, how far do they move? Well, the robber, it tells me, is moving at 3 meters per second. And I'm going to multiply that speed times how much time passes, which is 3 seconds. And when you multiply them, the seconds will cancel, and we'll get 9 meters. So this is how far the robber moves. R is going to move 9 meters. So the problem told me, well, initially, this distance from where the robber is to that corner is 11 meters. So initially this is 11. But now, after it moves 9, now the robber is going to be further. And that new distance is going to be 20. I don't just want to write 20 there because that distance is changing because the robber is moving. So I'm going to assign a variable to it. Okay, so maybe I'll call this x. Okay, and at the instant we care about, the x value is 20, but I don't just want to write 20 without a variable because it is changing. All right, and then for the police officer, it says they were initially 30 meters away from the intersection. So initially this distance was 30, and how far does the police officer move? Well, they're running at 5 meters per second, and we multiply that by the 3 seconds, by the time. So the seconds will cancel, and this gives me 15 meters. So that's how much P moves. So that distance used to be 30, and they move 15. We'll do 30 minus 15. So the police officer is closer. I'll move this P here. Okay. I'm going to assign a variable to that length as well, because it is changing, because the police officer is moving. But at the instant that we care about, this Y value is going to be 15. Okay. The question is asking what rate is the distance between them changing. So let's draw that. So I'm going to draw a line between them. And that's changing, so I'm going to assign a variable to it like Z. All right, so we got our picture. We are now ready to write down the rate that we know and rates that we want to find. Okay, so we know dx dt. It tells me how fast the robber is moving. That's going to be 3. And it's going to be positive 3 because x is getting bigger, because the robber is moving away from the intersection. X is getting larger. We also know dy dt. That's going to be negative 5, because the police officer is running at 5 meters per second, but that's shrinking y. It's making y get smaller. That's why this is negative. And then I want to find dz dt, the rate at which the distance between them, this straight line distance, is changing. Okay, so we are ready for the equation. So equation. So we have a right angle here. So let's do some Pythagorean theorem. We'll get x squared plus y squared equals z squared. I can't plug in for any of these variables yet because none of them are constant. All right, let's take our derivative. So let's take d dt of everything. So d dt of the left equals d dt of the right. And I have x squared plus y squared in here and z squared in there. So when we do this derivative, we'll get 2x dx dt plus 2y dy dt. This is implicit differentiation. And on the other side, we get 2z times dz dt. All right, and now we want to plug in for stuff that we know. So this is where drawing the specific triangle at the instant that we're talking about is going to help. I'm going to make this right triangle. And at this instant, this horizontal length is 20. That vertical length is 15, and then the hypotenuse is going to be z. So if I do some Pythagorean theorem, we'll get 15 squared plus 20 squared equals z squared. And simplifying, the left-hand side becomes 625 equals z squared. And if I square root this, the square root of 25, square root of 625 is 25. And as we've seen before in problems like this, we don't need a plus or minus. We don't need plus or minus since the z is a length. Since z is a length. All right, let's plug in. So we'll get 2 times x was this horizontal distance, 20. dx dt was given to be 3. And then I get plus 2 times y. The y values that vertical length, 15. And dy dt was also given as negative 5. And that's going to be equal to 2z. Z we now know is 25. Times dz dt, and dz dt is what I'm trying to find. Okay, so simplifying this first term, 2 times 20 times 3, that is going to be 120. And then I'll get minus 150 equals 50 dz dt. All right, let's continue to simplify. So 120 minus 150, that equals negative 30. So if I divide by 50, we get dz dt equals negative 30 over 50, which is negative 3 over 5. So the last thing I need is units. The units of length in this problem for z, because z is on the top, were meters, and units of time for t on the bottom were seconds. All right, and that is my answer. That's the rate at which z was changing. The distance between these two people was changing. And the fact that this is negative means that z, that distance, is decreasing.